Bismillahirrahmanirrahim. This is lecture 8D of Real Statistics and Islamic Approach. In this lecture, we will discuss the properties of the binomial distribution, which is one of the most important discrete distributions. The reason this distribution is important is because it is the simplest possible probability model. So we describe it by saying that at time 0, many different outcomes can emerge at time 1. So we group these outcomes into two sets. Call one of these sets success and all others failure. So now there are only two outcomes. Actually, there are lots of outcomes, but they are merged into two. So see, we have a few successes and one failure, another failure, more successes, more failures, more successes. So this is the lots of events, but when we group them, then we end up with only two events. And suppose that, to simplify, that all branches has equal probability, then we can say that probability at time equals 0 of success at time 1 is P, any probability. In this diagram, it would be 4 out of 7. And similarly, probability at time equals 0 of failure at time 1 would be 1 minus P, or 3/7 in this diagram. So there are two outcomes, success or failure, and they have two probabilities, but these two probabilities must sum to 1. Next, suppose that this model just keeps repeating at every time period. So the exact same model, initial step, we say that, okay, success occurs with 60% and failure occurs with probability 50%, 40%. And then at the next step, regardless of what happens, suppose that we succeeded in the first step, again we have another 60% probability of success at the second step and 40% probability of failure at the second step. Similarly, even if we have failure at the first step, we again have exactly the same model at the second step, 60%, 40%. Now we go on to the third step, and again the model repeats. Regardless of which of the 4 outcomes occurred in the second step, at the third step we have the third success in the top branch. Note that so this event, which is 3 time positions later from 0. So if you want to calculate the probability of this sitting at time 0, then we have the event that S1, S2, S3 follow each other. That is, success occurs at time period 1, followed by 2, followed by 3. So then the probability is just the probability of the product of the branches. So it's 60% times 60% times 60%. Now, the second possibility is that we have failure at the third step. So 2 successes followed by failure. The probability at time it equals 0 is just 60% times 60% times 40%. Then we look at the second branch. In this branch, we had success at the first period, then failure at second period, followed by success. So we just multiply the 3 probabilities, 60% times 40% times 60%, to get the probability of this particular branch at time equals 0. And similarly, on this branch, if we have failure at the last step, then we have 60%, which was the success at first step, times 40%, the 2 failures that followed. And again, this is the probability at time equals 0. Now we go on to the next branch, the bottom branch, in which failure occurred at the first step. Then it was followed by 2 successes. So the probability of this will be 40% times 2 success probabilities, 60% and 60%. If last step gives you failure, then you have failure, success, failure, and that will be 40%, 60%, 40%. And the same type of calculation occurs when you have 2 failures in a row followed by a success. So that would be 40%, 40%, 60%. And 3 failures would be 40% times 40% times 40%. So all of these are calculation on these branches. This is made simple because everything is independent. The probabilities don't depend on which branch you are on, and exactly the same structure is repeating. So this is why this is the simplest possible probability model. So t equals 3 and 60%, 40% were just given as examples. T can be any number and the probability of success can be any probability. So now we do the calculations in this general case. So we see that the number of outcomes doubles at every stage. So if there are n stages, then the number of possible outcomes will be 2 multiplied by itself n times, or 2 to the n. When we want to calculate the probability of these outcomes, then one thing is to note is that because of independence, the sequencing does not matter. So if you have a particular sequence of length n, we will call this O for the outcome. It is like success, success, failure, success, failure, and anything following any kind of mixture of failures and successes to the end with n different outcomes. Then in order to find the probability of this, we just have to count the number of successes and also count the number of failures. So let's say that there are k successes and n minus k failures, because the two numbers must add up to n. So then the probability of this outcome is p raised to the power k, where p is the probability of success, and 1 minus p raised to the power n minus k. We just multiply all of the probabilities of the successes and all of the probabilities of the failures together to get the final probability. With this model in place, we can now define what is known as the binomial random variable. And the notation for this is that x is called a binomial random variable if x is, and this is written as by np. X counts the number of successes in n trials, where each trial has success probability p. So the number of successes can take value from 0, 1, 2, 3, 4 to n. X is an event, it is not an outcome. There are many different outcomes on which the same event occurs. Like if you have in 2 trials, if you have head followed by tail, or tail followed by head, or success followed by failure, failure followed by success, there is one success. So both of these two outcomes correspond to the same event. So X is looking at the event which counts the number of successes regardless of the order in which they happen. So for each particular trial which has k successes, the probability is p to the k times 1 minus p to the n minus k, that we have already seen. But to get the probability that x equals k, we have to count all of these trials and add them up. So all of the different outcomes on which x equals k, each of them gives you a probability for x equals k, and we have to add up all of these in order to get the probability. To find out how many cases there are, we need to find the famous formula which is called the n choose k formula. So consider this sequence of 10 outcomes. So we are thinking of n as 10, and in this sequence we have ht, htt, and then httt, or successes, 2 successes in the first 5 and 2 more in the second 5. So we have 4 successes and 6 failures. Each head counts as a success and each tail counts as a failure. We are flipping a coin now. So the probability will be p to the 4th times 1 minus p to the 6th. So that's we have already computed. Now the question is, how many sequences are there in which there are 4 heads and 6 tails? So there are many possibilities, like the second one is shown here, 2 H's followed by 3 tails, and then 3 tails followed by 2 H's, and then there can be many others. So the general question is, how many ways can we put in exactly 4 heads into a sequence of 10 slots? This number is called n choose k, or 10 choose 4, and it is denoted as C of nk. Choose from n k slots. And it can be computed that this n choose k, which is also written as parentheses n on top, k on bottom, close parentheses, it can be shown that this number is n factorial over k factorial times n minus k factorial. A detailed derivation of this formula is given in the write-up of this lecture. But we will just take this for granted, that this is how many sequences there are. The goal here is to learn the concepts and not the formulas. The formulas can be computed by Excel, but understanding cannot be achieved by the computer. So the student is supposed to understand what is happening and not necessarily be able to compute. He can give the formula to the calculator. So once we have the binomial probabilities in hand, then we can derive the formula for probability x equals k. So just to put everything together, we use the symbol x is distributed as binomial with n trials and p as the probability of success. This means that x is the number of heads in a sequence of n flips where the probability of heads is p. Heads is equivalent to success. X is a random variable. It can take any value from 0 to n. That is the total number of successes in n trials. The maximum can be n and the minimum can be 0. Now, what is the probability of exactly k successes, where k is any number between 0 and n? So to compute this, we need to find out Cnk, the number of ways to put exactly k heads into the sequence of trials. Then for each such trial, which is a sequence of heads and tails in which there are k heads and n minus k tails, the probability is p to the k 1 minus p to the n minus k, and the number of such sequences c and k. So the probability that x equals k is n choose k, which is n factorial over k factorial times n minus k factorial, multiplied by the probability of one of these outcomes, which is p to the k times 1 minus p to the n minus k. So this is the derivation of the formula for binomial probabilities. So we have not focused very much on how we compute these binomial probabilities, because what is more important to learn is what these probabilities mean. How does the binomial random variable behave? What can we expect to see happen when we have a binomial probability model for a sequence of events? So the practical implications of probability in the real world is, if that there are two events, one of them has more probability, then it is more likely to happen. That is how we will think of a probability model. If the probability of some event is bigger than 50%, then it is more likely to happen than not. Now, if the probability of the event is between 90% and 99%, then we can say that it is very likely to happen. And if it's even bigger than 99%, then we can say it's almost a sure shot. All of these are just qualitative ideas. We attach these numbers as rough guides. The probability is used in an intuitive and qualitative way. It is not used in a precise quantitative form when we use it in real life. As opposed to this, the standard theory of decision making under uncertainty these days is called rational decision making, and this theory says that we use exact numbers of probabilities and exact values of outcomes, and we do all the calculations required to do quantitative decision making. This theory is very deeply flawed, and we are trying to develop an alternative here. So in the next few slides, we will study how binomial random variables behave, so that we can recognize how this behavior occurs, and we can check with actual observations in the real world to see if this behavior matches what our model says. And if the match between what our model predicts and what happens in the real world is good, this will provide some indirect confirmation of the model. If the match is not good, that means that our probability model is wrong. And so this will also give us some information, because the failure of model also provides us with information about what is happening in the real world. So either we can reject the binomial model because the predictions do not match what we see, or we can tentatively accept it, that saying yes, there is a good match, but later on this might change. So then how do we match probability models to actual real-world data? We can't really verify the probability model in all its details because it tells us about lots of things which never happen. Like in the probability, the binomial model, there's only one branch which will be taken, and there are 2 to the n minus 1 different branches which were never taken, which will never occur. So we won't know whether or not they could have happened and what probabilities they would have had. So the match probability is only for some very small number of observable outcomes. It is impossible to directly observe the truth of such models. But we can look at the predictions, we can look at what the model says is likely to happen, the 99% confidence interval, and if observations come within this range, then the model is acceptable. If the observations fall outside the range of 99% confidence, then the model is predicting that this will happen with 99% probability, but it doesn't happen. So then we have reason to doubt the model. The model is not reliable. So now we will look at the binomial models to see what are the 99% probability events. What types of predictions do we get from these binomial probability models? So if we take n trials, then how many successes do we expect to see? It turns out that the modal value is the one which has the most probability, is n times p. That's simply because on each trial, the probability of success is p, so about p% of the time you have a success, and 1 minus p% of the time you have failure. So suppose n is 100, then p% of these trials would be successes, ones, and all the rest would be failures, which is counted as 0. So you will have exactly p times n, or np successes. Now, so one might think that the prediction of the binomial model is that the most likely outcome will occur. But this is not true, because even though it's the most likely probability, this probability of the modal event goes to 0 as n goes to infinity. And so we will see why this is so, and then we will generate the most likely events, the confidence intervals. So here's a graph of binomial probabilities when n is 20 and success probability is 25%. So in this case, the modal value is np equals 5. In 20 trials, if you have 25% success probability, then you will see 5 successes and 15 failures. These probabilities have been computed using the formula that we have developed, but the probabilities has been implemented in Excel. So we can just put in the formula and ask it to give it the probabilities. Also, Excel has produced a graph of these, and we can see that at x equals 5, the probability is 0.202331, and on the graph, this is the highest bar. So the probability is highest at the modal value, and it declines on both sides. This is called a unimodal distribution. More interesting is the fact that the probability becomes virtually 0 following 10. At 10 it's 9 in 1000, and at 11 it's 3 in 1000, and it keeps going down very, very fast. So in effect, if we say let's look at probabilities which are ignore probabilities below 1%, then we can say that basically the range from 1 to 9 is the range of central values where the outcomes can occur. So if I have a probability model which says that n is 20 and p is 25, and I observe something like 15 successes, then I can reject this model because it's outside the range of the values which are likely. So this is the thing that we can reject for 0 and reject this model for values above 10. And in the middle of in the center of the range, the central values 1 to 9 are the ones that are predicted by this model. Next, we consider a case with a bigger n. Suppose that n is 50, the probability is 75%, then NP is 37.5. Now this time the modal value is not an integer, so the highest value can be either 37 or 38 according to certain rules. So it turns out that in this particular case, the mode is at 38. The highest probability is 12.9%. And this is again a unimodal distribution. And this time, if you look at where the probabilities are high, you see that for 3 decimal places, the range from 27 to 46 has some value. It has a 1 in 1000 probability. But after outside this interval, the probability is less than 1 in 1000. So between 27 to 46, we can consider this model, but if the values are above 46 or below 27, then we would reject this binomial model. We increase to n equals 100 and set the probability p to 21%. NP is now 21. 21 is the modal value, and it has probability 21 has value 9.8%. As a unimodal distribution, the central values range from 9 to 34. In this range, the probabilities of the outcomes are above 1 in 1000. Outside this range, the probabilities of the outcomes are less than 1 in 1000. So this is the central value. So if you, to summarize, suppose I have a probability model for a sequence of 100 events. These could be like 100 patients which are given drugs, and we think that this drug has 21% efficiency, 21% of the people should be cured. So if this value is, this is our null hypothesis, and so if we see anywhere between 9 to 34 patients cured, then we will say that this null hypothesis is accepted by the data. It is not rejected by the data. Outside this range, if only 5 patients are cured, or if 50 patients are cured, then we'll say no, the efficacy of this drug cannot be 21%. It might be higher, or it might be lower, it might be different, or the model might be wrong for some other reasons, but it cannot be the case that this drug has efficiency 21%. So this is what it means to reject the model. Finally, we'll look at a case where n is 500, success probability is 18%. If we multiply 18%, take 18% of 500, we get 90 trials. 90 doubles to 180 when you multiply by 2. So the mode is 90 successes out of 500 trials. And at 90 successes, we have probability 4.6%. And the central range here is 60 to 120, about 30 units on both sides of 90. Outside this, the probability is less than 1 in 10,000. So basically, if we are within this range 60 to 120, then we should accept this model, or at least it has some plausibility. If the number of successes is more than 120 or less than 60, then the idea that this is a binomial model of trials with 18% success probability can be rejected. 18% does not match what we see in the data. So what do we learn from this data, from these pictures of binomial probabilities? We learned that the modal value is NP, and we have seen why this is so. But the surprising thing is that the modal value, the probability of the mode, goes to 0%. So this is surprising, but you can understand it because as n is increasing, the probability spreads out over a large number of numbers. And as the probability spreads out, each probability goes to 0, but the sum remains to 1. Like suppose you have 10 outcomes, then each outcome can have 10% probability. But if you have 100 outcomes, then each outcome can have 1% probability. So that's why as the number of possible outcomes increases, the probability of each outcome decreases. So the most important prediction of the probability model is not that the modal value will occur, because it's a low probability event, but that the range in which most of the probability is concentrated will occur. So at 20, the range was 1 to 9, which is about 40%. At 50, the range decreased a little, increased to 27 to 46. But as a percentage, it decreased to 38%. When you had 100 trials, the range of acceptable values was 9 to 34. So the size of the range is 25, which is bigger than the size 19 earlier, but as a percentage, it is smaller. Finally, with 500 trials, we had the range was 60 to 120. As a percentage, this is 12%. Although basically the interval of values, the set of numbers which can occur, keeps growing. It was 8, 19, 25, 60. But in percentage terms, it keeps shrinking. 40%, 38%, 25%, 12%. So if we want to make a forecast of what will happen, in percentage terms, we will become more and more accurate. But if we look at the absolute range of numbers will be increasing. Some difficult mathematical theorems lead to the following asymptotic results. Asymptotic means large n. If there are a large number of trials, then the proportion of successes, x is the number of successes, you divide it by n, so that will be a percentage. This is the observed proportion of successes, which is what you see in the trials. This will become close to the true probability of success, the probability in the model, the theoretical probability. The central limit theorem tells us that if you define SD, standard deviation, as square root of n times p times 1 minus p, then the difference between the p and the theoretical probability of success in our model and the observed probability of success, the number of successful trials out of n, this difference will be between minus 2 SD and plus 2 SD with 95% probability, and this difference will be between minus 3 SD and plus 3 SD with 99.7% probability. So this gives us the central values, the range over which x over n varies, and this tells us what we can believe, what the probability model predicts. The probability model predicts that with 99.7% probability, the number of successes, the ratio of the number of successes to the number of trials will not be different from p by more than this range, which can be computed. So based on this prediction, we can assess whether or not a probability model is working, because if this outcome is within this range, then we can say that the probability model works. If it's outside this range, then we can reject the model.